Hi all, I'm back with my crazy homemade document camera. I wanted to talk to you about one of the methods for solving systems of equations. This method I'm going to highlight is called substitution. This particular system, and this curly bracket here, indicates that these two are linked in a system. This system isn't really set up easily to graph, right? Because I could easily graph this. It has a y-intercept of 5 and a slope of 2, but sort of graphing these linear equations in that are set up in standard form are kind of a pain for students. I do think it is worth it to teach them how to isolate y, right? Let's subtract 4x over to the other side. We could divide everything by 2 and get y by itself. That's a good exercise for students for later in mathematics. But for this one, I'm going to use the substitution method. And the reason I'm going to use that is because I have this y here that's by itself, right? So I have a y here. I tell students, I know that this y is worth 2x plus 5, right? It's the same. This equal sign means that these two things are interchangeable. That's difficult for students to sort of conceptualize. The symbolic representation of functions is hard for students that don't have sort of that abstract reasoning yet. But I tell them it's sort of like a $20 bill and two $10 bills, right? They look very different, but they are the same. So essentially, anywhere I see a y in this second equation, I can substitute this 2x plus 5 in, right? I can substitute that in because it is worth the same as that y. Those two things are equivalent. So when I substitute it in, I end up with 4x, right? Because that's just the same, plus 2. And then the only thing that leaves me is that y, right? That y goes away, but that 2x plus 5 gets substituted in there, right? He replaces our y. This is sometimes tricky for students who have sort of like the visual issues because it does get very big. They do sort of lose track of what this equation looked like to them visually when that comes out and becomes a little bit bigger. I think highlighting, I've used index cards where we kind of pull the card out and put a new card in. That can all be really helpful. When you look at this, now we have, the reason we did this because now we have all x's, right? And before we couldn't really do anything to solve these, but now we have all x's. I'm sorry for that refocusing that keeps happening. And it's just a really big equation to solve. For some students, this is a great method because they are very fluent in these step-by-step equations. For others, this is very tricky. When I use a distributive property, I get plus 4x plus 10 equals 34. I am going to combine these like terms to get 8x plus 10 equals 34. You all did amazingly with your equation solving, so I'm not going to spend too much time here, but I end up with 8x equals 24. When we divide by 8, we get x equals 3. Now, we know with systems that a point of intersection is our solution. X equals 3 is not a point on the coordinate plane. To be a point on a coordinate plane, we need an X and we need a Y. We need to know like the other part of that location, right? We can't play Battleship with just an A. We need an A5. So we need that second coordinate. So I'm going to use this and substitute it back into this equation. The reason I'm going to choose this equation is it's the easiest. You could choose either equation and you'd get it right. And I do that with students. I show them that, hey, it doesn't matter which one. You're still going to get the same answer, but I am going to choose this one. So I took out that x and plugged that 3 in to get me to my final answer, which is y equals 11. So if I was to graph this, and this is a great exercise as well, is to go back and graph it to prove it to students you weren't lying, right? These two equations will intersect at 3, 11. So this is a system that has one intersection point at 3, 11. If you were to have an equation where there was no solution, where it was those parallel lines that I talked about in the last video, you would have something like this. Let me think of one off. And let's say All right, so with this one, I'm going to show you real quick how I'd substitute. I'm going to substitute this, and for this guy, and we get negative 10x plus 2 times 5x plus 1. One of the biggest mistakes students make, right, is that they plug this in for x because they're like, oh, the x's match. But you're actually taking the y out and putting this in. What'll happen is if they plug that in for the x, they'll still end up with an x and a y in the same equation, and they won't be able to do anything. So that's sort of that check for them. So I have negative 10x plus 10x plus 2 equals 3. Well, what happens here in these types of systems is you get 2 equals 3. We know that's not true. If you get something when you solve by substitution that is not true, this is one of those that I talked about graphically that would have no solution, okay? If you graphed these two lines, which I didn't put my bracket with them, if you graph these two lines, they would be parallel. They would never intersect. So you'd get no solution. And I'm not going to run through another one, but if you got something like 3 equals 3, where it is always true, your solution would be all real numbers, okay? If this was the solution to the system. So this would be one of those cases that I talked about in the last video where it's the same line, it intersects on every point. Those ones are pretty obvious usually, but it might not be as obvious if it looked like this. Okay, these are actually the same line. If you solve them, when you add 10 to both sides and divide by 2, you get 5x plus 1. These would have a solution of all real numbers because they are the same line. They intersect everywhere. So that's substitution. Let me know if you need more examples.